We all assume that sustainability science should aim at trying to clarify the course of action in order for us to address some of the most complex problems that we face as society, climate change, again, the water crisis, etc. But what I would like to say today is that I believe it's the other way around. So when sustainability science is done rightly, the course of action becomes unclear. And this is the take-home message that I'd like to convey today. And why is that? There are very many reasons. There are I think there's one philosophical reason, and there's also one empirical reason as to why sustainability science, when done right, tends to increase rather than to reduce uncertainties. The first one is that sustainability science is basically normative. This means that it not only aims at discovering facts, these are describing what is out there, but also at the same time, it aims at defining what ought to be. It deals with our visions of the future. And of course, our visions of the future are basically defined by our own values, our own ethical stances. And so, since values shape the production of knowledge, the knowledge that sustainability science produces sometimes is conflicting. And this is because, our perspective of what is fairness, what is justice, our notion of risk is not objective. We all have our own vision of the risk that we are willing to take on a given problem. And so when this is taken into account, you realize that there is no single set of values that define one given problem. There's a lot of legitimate perspectives that can say important things about a problem of interest. And so sustainability science, if it really wants to make sense of the complexity of the world out there, should try to avoid epistemic closure. And so should try to embrace a wide range of legitimate perspectives in order to do justice to the plurality of views that exist out there. And this is the philosophical reason why sustainability science is at its best when it expands, and so when it embraces uncertainties rather than when it clarifies courses of action. And then there's an empirical justification for this, and it's that sustainability science is already very good at expanding uncertainties. We've seen this in many fields, right? So in climate change, water resources, food production. I'm going to put some examples for this. But in all these fields, sustainability science over the last 40, 50 years has increased uncertainty significantly. So the increase in our knowledge of how these problems work and on the impact of these problems has gone hand in hand with an increase in uncertainties. And then, since many of these problems are tackled using mathematical models, also it's important to understand how mathematical models work. And in that specific case, the assumption has been that if we want to clarify the course of action, this is to know what we should do in order to tackle climate change, we should collect more and more data in order to have more and more detailed and accurate mathematical models, with the assumption that more detailed mathematical models will sort of narrow down the space of options. Well, it's actually the opposite, as we will see. So the more detailed mathematical models get, the larger the uncertainty they produce. They produce more uncertain estimates. And so from an empirical perspective, sustainability science is really, really good at fostering skepticism, at doubting evidence, and so at opening up debate. It's not as good as closing it down. And I think that's something good. I want to introduce you to Daniel Sarevitz. He discussed much better than me all these issues and all these challenges in a paper that is very, very cited, that will appear in the reference section at the end of it. he's of the opinion that, when you throw science to an environmental problem, the controversies get worse. So science don't sort out environmental controversies. It actually makes them worse. And the reason why it makes them worse is because science is so good at extracting information from the real world that depending on your academic background, whether you are an ecologist or an atmospheric scientist or a geologist, the information you will extract from the real world will provide a different perspective of the problem. So for instance, imagine now climate change, right? Daniel Sarewitz says that if you are a geologist, you will see climate change in the geological record as a sort of, you will see the consequences, so to speak. You will not see the causes. You will see the consequences in the geological record, and you might be able to study it via, isotopes and tracing, fossils, etc. And so to you as a geologist, climate change appears as a sort of an indeterminate, kind of contingent process. But if you're a climate scientist, basically you're interested in identifying the causes. You want to see what drives atmospheric change. And so to you, climate change will pop up as a sort of deterministic process. Now, both visions of the same problem are legitimate. There's no right or wrong perspective here. But both visions provide a different interpretation of the same phenomenon. And so these different interpretations also open up different possibilities to implement this knowledge for action in the real world. And another example would be, an increase in temperature due to greenhouse gases. So for a climate scientist, this phenomenon might not be enough to justify action in the real world, because just a slight increase doesn't disrupt the entire climate system. The climate system is not fundamentally destabilized, right? But for an ecologist that works in a patch of land, very small temperature variations can indeed change ecosystem functions. And so for an ecologist, this slight increase in temperature might justify the need for rapid policy action. And so again, the same phenomenon, the same problem here, depending on where you come from disciplinary-wise, might lead you to propose a specific initiative, in that case, a more cautious approach, or then more rapid policy action. So the more you study a complex topic, the more you need to mobilize different lines of evidence, the more you need to mobilize different disciplines, and then uncertainties increase. And one example that uncertainties that have increased after trying to mobilize different sources of evidence is the climate sensitivity concept. So climate sensitivity, as you might be familiar with the concept already, but it's basically the increase in temperature that will happen if the amount of CO2 in the atmosphere is doubled, right? So there's been many studies that have tried to see how this metric will evolve in the future. They've basically used mathematical models. But interestingly, the more detailed these models have become, the more data we've fed into these models, the larger the uncertainty has gotten. And so here I show two different plots. The first figure on the left shows the results of CMIP3 models. This is IPCC4. And you see the spread here is much narrower than the spread that we got in the CMIP5 models for IPCC5. In here, the models, where they used approximately 20 models that were quite simple in terms of atmospheric ocean feedbacks, and also they were at a sort of a 250 kilometer resolution, and then in the next iteration they used 60 models at a 100 kilometer resolution with more detailed feedbacks between ocean and the atmosphere, and also with vegetation dynamics, etc. So even though we had better data and we had more knowledge of the process, this knowledge didn't lead to more precise estimates, but the other way around. So uncertainties and the range of possibilities expanded rather than reducing. And the reason that this happens is a little bit hard to explain, but basically, the more detail you put into models, the larger the uncertainties get, because the number of parameters and the uncertainties that characterize these parameters compound. And so by adding more parameters, this is by describing the process of interest with more details, the uncertainty sort of increases. This is a numerical experiment that we did using different combinations of parameters in different models in order to see what happens when you increase the dimension of models. And we saw that the general trend is simply that, the more detail your model gets, the more uncertain the estimates become. Because the more parameters you have in your model, the larger the uncertainty space. Meaning that if you have two parameters, the uncertainty can be conveyed by parameter 1 and parameter 2, and by a combination of both. This by an interaction effect between both. If you have 3 parameters, you have the effect of parameter 1, parameter 2, and parameter 3. The effect of a couple parameters, parameter 1 and 2, 1 and 3, 2 and 3, and then the 3 together. And so interactions really explode by adding parameters, and interactions are what drives uncertainty in mathematical models. An example of this, I want to now talk a little bit about planetary boundaries. Because it's an example of how sustainability research has sometimes excluded alternative views and led to unwarrantedly precise estimates that have been used to guide action. You might have seen this. There's this narrative that says that we humans have crossed the freshwater planetary boundary. And since we have crossed the freshwater planetary boundary, we need to do something immediately, because if we don't do anything, no person, place, economy, or ecosystem will be spared, as they say. And so we need a radical transformation of the economics of water. And the Global Commission on the Economics of Water, led by Mariana Mazzucato and Johan Rockström, have proposed the adoption of free market policies for water. The thing is that this policy action is based on a model that has several highly questionable assumptions, I think, because it kind of narrows down the range of legitimate assumptions that can fit into the model. I don't know why the equation doesn't show, it really doesn't matter, but the most important thing is that the model that they use to sort of justify the need for these free market policies for water assumes that everybody on Earth consumes 3,000 kilocalories daily, for instance. And this is something that, of course, conditions the amount of water that is withdrawn for food production. Because if you assume that there's no starvation in the world, that everybody eats as much as an American, 3,000 kilocalories, then the amount of water that is consumed in the world is very large. And so if you define a planetary boundary for water, chances are that the number that the model will produce will be beyond this, because of this assumption. And then, of course, the assumption that there's 80% of vegetable diet and 20% based on meat is also a simplification, because the percentage of meat and vegetation that people consume is very different. So all these assumptions are kind of normative in a way. They are normative. They are not really scientific. This is just normative assumptions and normative regulations that they've sort of ingrained in the model and of course have conditioned the final estimation. So as soon as you take into account the uncertainties in the amount of kilocalories that people consume on a daily basis, the variety of diets that exist in the real world, because not everybody, relies on an 80% vegetables and 20% meat. And when you take into consideration also the fact that for producing 1,000 kilocalories of meat, depending on the meat you use, you will use more water or less in producing this meat, then things start to become a little bit more ambiguous. And so if you run the model that they've used again by propagating all these uncertainties, then it's not clear at all that we've trespassed the freshwater planetary boundary. In fact, most simulations suggest that we haven't because of this uncertainty. This is the simulations in gray are simulations that suggest that we have not trespassed the freshwater planetary boundary, while those in red suggest that we have. And so basically, as soon as you start implementing real-world complexity and different values in these models, the curves of action becomes a little bit more blurred. Okay? It's probably more realistic, but less helpful for policymaking. Then there's another example of how uncertainties usually get larger with further research. This is an example on global irrigation water use. Global irrigation water use is very important because irrigation is the sector that consumes the most fresh water of all, and so modelers have tried to estimate the exact amount of fresh water that is withdrawn for irrigation for a long time. Since the 1970s, they've been very worried about uncertainties because it's quite hard to compute this metric. And so they've made a lot of calls suggesting that we need to acquire better data, that we need to design better models, invest more funds in remote sensing, in mapping irrigated areas better, etc. And so we wanted to see, in my team, whether these efforts have actually delivered and whether all this investment in research has actually constrained the range of estimates for the amount of global withdrawal, global irrigation withdrawal. And so what we did was we collected all the estimates of global irrigation water withdrawals that were made over the last 50 years, close to 1,200 estimates. And then we designed a research approach in order to tackle this question. Okay? Have uncertainties been reduced through research? Of course, as you see, this is quite an ambiguous research question. It can be addressed in many different ways, right? For instance, if we focus on the estimations for 2000, maybe the estimates will have, the uncertainty will have been reduced, while if we focus on the estimates for 2050, the estimates will have increased. So depending on the target year that we focus on, the results might be different, right? So what we did was to sort of define all possible research designs that addressing this question allows for. And we kind of conducted 3,500 research designs in which we kind of changed the target year. So we calculated the evolution of uncertainty for studies that estimated global irrigation water withdrawals for the year 2000, but also for those that estimated global irrigation water withdrawals for 2050 and 2100 and 2025 and so on and so forth. And then, of course, we also assess the uncertainty in the beginning of the studies. For example, in that specific case, we collected all studies published between 1990 and 2000 that estimated global irrigation water withdrawals for the year 2000. And so we have three studies here. 1, 2, 3, 4, 5, 6 studies here, 1, 2, 3, 4 studies over there. And then we assessed the spread. Okay, the spread. This is the uncertainty. If we see that the spread was increasing, we assume that the uncertainty has increased through research. But of course, this is not the only year that we could assess. So we also assessed 2050, 2020, 2035, and so on and so forth. And also we changed the definition of the bins. This is a 10-year span, but we also assessed, what happens if you use a 15-year span or a 20-year span. And so we took into account also the uncertainty in the design of the methodology, which is rarely taken into account. And so we observed that after running these 3,500 simulations, most of the simulations suggested that uncertainty has increased, not decreased. And so research over the last 50 years has produced knowledge that has gone alongside with larger uncertainties, mostly. And what's also very interesting is the fact that we discovered that uncertainty is not really an objective property of the data. It's also something that emerges from the act of measurement itself. Okay, so how do we measure uncertainty? We can use the range. This is the minimum and the maximum of a given spread of values. But we can also, for instance, use the coefficient of variation, which is another metric, or we can use the standard deviation, etc. And so depending on the metric that you use, you get a different understanding of uncertainty. And so for the same research design, for the same spread, we observed that depending on the metric that we use for uncertainty, we could have an insight that suggests that uncertainties have increased. If we use, for instance, the metric known as the range, but also that uncertainties have decreased at the same time if we use another metric, the coefficient of variation. And then also that we don't know what happened with uncertainties, it had an unstable evolution. Okay, so uncertainties are not really objective because in order for us to make sense of them, we have to use metrics that consider specific features of the data. Okay, that's also quite important to stress. Another example of how the production of knowledge goes alongside with larger ambiguities is the research that I'm also going to present today. I guess that you guys have heard about one of the most famous sustainability statistics. It's mentioned everywhere. It's the assumption that irrigation withdraws 70% of all freshwater withdrawals in the world and produces 40% of all crops. And so the assumption is that irrigation agriculture is extremely important for food and water security because the numbers suggest so. What we did was to collect all the literature and see how this belief spread. The red dots basically are those studies that contain the statement that irrigation withdraws 70% and 40%. But don't provide any data to support this. So it's basically a statement that doesn't have any support. While the other dots are studies that cite the other studies to provide support for the statement that irrigation withdraws 70 and 40%. So what we observe is that this belief that has spread so much has no true empirical support. It's just supported by 1.5% of all these 3,500 papers that we sort of examined. And so it's a belief system that has spread through hearsay, mostly. And as soon as we start to dig into the data, we observed that actually irrigation can withdraw between 45–90% of all freshwater withdrawals and can produce between 18 and 50% of all crops. And so irrigation can be either highly inefficient, while at the same time, irrigation can be also very efficient for global and food and water security. And so all policies are supported by the data. So the available data supports all possible policies here. And then this last plot suggested also how, depending on the perspective that you have, you will extract specific information from a phenomenon or another information. Basically, here we asked irrigation scientists to mention the first concepts that they think of when they think about irrigation, but we also asked the same question to traditional irrigators. And while scientists just mentioned technical concepts, irrigators mention emotional concepts. This relates to something that has been said already. So irrigators mention childhood, satisfaction, ancestors, grandfather, father, etc. And so depending on the knowledge that you mobilize here, you get a different understanding of what irrigation is. And so just to wrap up, sustainability science is really good at unfolding the complexity of our world. And so for closing debate through prescriptions, regulations, it's a little bit like shooting ourselves in the feet, right? Because favoring advocacy, being an activist in that sense, may lead to losing social legitimacy and indeed to science denial by specific constituencies. And so, yeah, sustainability science is very powerful to provide evidence that in some situations science is not the way to guide action. It's basically something that cannot allow us to, cannot help us decide what to do. And so what we have to do is simply be very open and transparent about the values and the politics and the possible futures that we want. That's it. Thank you very much.